This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Chapter 4 of Curious Math, Numbers that Change the World. Prime numbers, the building blocks of math. In this chapter, you'll learn: explain what makes a number prime and its properties. Let's dive in. Right now, almost every secure website you visit is protected by secrets built from just a few special numbers. You unlock your phone, send a message, buy coffee online. Each time, hidden primes are at work. In this episode, we'll pull those invisible numbers into the spotlight. Prime numbers feel abstract, yet they show up in very concrete places. Your browser, your banking app, even some digital passports rely on primes so large they'd stretch for pages if you tried to print them. One record holder from 2023 has 24,862,048 digits. Reading it aloud nonstop would take weeks. To see why primes matter, we'll zoom in on their mathematical role and then zoom out to their technological impact. Mathematically, primes are the unique ingredients behind every whole number. 60 breaks into 2 times 2 times 3 times 5, 91 into 7 times 13, and so on, always in one definitive way. Technologically, this uniqueness and the difficulty of reversing it at huge scales are what let protocols like RSA and elliptic curve systems keep secrets safe, at least until quantum algorithms force us to rethink everything. So, how big is big in this world of number-based security? A typical 2048-bit key used in practice corresponds to a number around 1,617. That's larger than the estimated number of atoms in the Milky Way, often put near 1,068 to 1,069. Over 90% of secure sites in 2023 relied on such keys via TLS, according to Mozilla's telemetry, meaning your everyday browsing leans on these gigantic values. Mathematicians aren't just playing with toys here. When a new record prime with 24,862,048 digits is found, it helps test algorithms that later influence how fast and safely we can generate keys. Here's a key structural idea we haven't used yet: direction. Going from primes to their product is easy. Going backward can be brutally hard. Try this with small numbers first. Multiplying two primes like 101 and 103 in your head is annoying but doable. 101 times 103 equals 10,403. Now, reverse the task. You're only given 10,403 and told it is the product of two primes. Factor it. You might test 2, 3, 5, 7, 11, until you finally hit 101 and 103. The forward direction, multiply, is fast. The backward direction, factor, is slow. Scale that up. Replace 101 and 103 with two primes that each have 300 digits, and their product has roughly 600 digits. Checking all possible factors up to its square root would mean testing primes up to about 1,300. Even with better than brute force methods, the search space explodes. This asymmetry, easy one way, hard the other, is exactly what cryptographers formalize as a one-way function. Primality testing sits on the other side of this divide. Given a 600-digit number n, you don't need to factor it to see if it's prime. Algorithms like Miller-Rabin can very quickly say, definitely composite, or probably prime, using modular arithmetic tricks. They raise numbers to huge powers mod n, and watch for patterns that can't happen if n were prime. The AKS algorithm even guarantees a correct answer in polynomial time, though it's slower in practice than the best randomized tests used in the real world. This difference, fast to test, hard to factor, leads to an important subtlety. Crypto systems don't just need big primes. They need primes with no hidden structure that might give attackers a shortcut. Standards therefore require careful randomness sources and extensive screening. In 2012, the Debian weak keys incident showed how a tiny bug in randomness could generate only about 215 possible RSA keys. Attackers pre-computed all of them. Your phone, browser, and servers now rely on large-scale industrial processes for generating, testing, and discarding candidate primes at massive speed. Modern libraries can sift through millions of random 2048-bit candidates, discarding almost all of them to keep only those that pass repeated, stringent primality tests with vanishingly small error probabilities. A concrete way to see primes working is to walk through a toy key setup with small numbers. Suppose Alice picks two random primes, 137 and 191. Their product is 26,167. In a real system, she'd use primes with about 600 digits, but the pattern is the same. Multiply two secret primes to get one public composite. Bob and anyone else see 26,167. Only Alice knows the two primes behind it. Even in this tiny example, trying every divisor up to square root of 26,167, approximately 161 is tedious by hand. Jump to a 600-digit composite, and that trial approach is hopeless. Modern libraries automate a scaled-up version of Alice's step. They might generate, say, 5,000 random 2048-bit candidates per second on a server-grade CPU. Fast filters instantly eliminate over 90% because they're divisible by small primes like 3, 5, 7, up to a few thousand. The survivors go through repeated probabilistic tests at different bases. After 40 or so rounds, the chance a composite slips through can be pushed below 2 to 80. At cloud scale, clusters churn through millions of such candidates daily, discarding almost all, keeping only those that pass every check. In the next decade, expect prime-based tools to coexist with post-quantum ones. Browsers are already testing hybrid handshakes that combine, for example, X25109 with Kyber, so breaking either alone isn't enough. If a major quantum break appeared tomorrow, millions of VPNs, government archives, and cryptocurrency wallets using long-lived keys, some valid until 2040, could be exposed. That's why NIST is standardizing new schemes now and urging migration plans before 2030. Your data's safety will depend on how quickly systems retire old keys and algorithms. So your next step isn't learning a new theorem, it's noticing where these ideas surface. Password managers, Signal, and WhatsApp all lean on key exchanges thousands of times per day on a single phone. At internet scale, that's billions of prime-driven operations every hour. Your challenge this week? Skim one app's security page and see which algorithms it names. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!